In this video, we're going to look at a problem involving mass defect and nuclear equations. So here's our example. PO218 decays to Pb214 as part of the uranium-218 decay series, which is shown in the graph opposite. Now on this, we've got the atomic number along the bottom. We've got the atomic mass up the vertical axis. We start at uranium and go down through to lead. Now we're going to work out, we know a radioactive particle is released with 9 times 10 to the negative 13 joules of kinetic energy. First off, we're going to write a full equation for the change and determine whether the total energy is conserved. We're also given a variety of masses. We've got our polonium, we've got our lead, here's our proton mass, here's our neutron mass, our electron, and our helium. And note they're all in kilograms. Okay, so we're going to write the full equation for this reaction. So first off, I've got to find polonium-218 on my decay series. So as I look all the way through, here it is. So I'm just going to underline it so that you can see it. I've then got to find my lead-214. Well, that drops down just below it, and I can see that it's dropping down, giving off an alpha particle. Alright, so from now, I can now write my full equation for that reaction. So 218 polonium, and it's got an atomic number of 84, and I can read that off by going down to that bottom number. That's going to give 214 lead, or 214 Pb, and has an atomic number of 82, plus an alpha particle, which we've determined from our decay series, and we presume that there may be some gamma radiation which is coming off. I'm just going to put on 4 and 2 because 214 plus 4 makes 218, 82 plus 2 makes 84, so it's now balanced, noting that alpha particle is a helium nucleus. So now we're going to determine whether the energy is conserved. Alrighty, so in order to do this, what we're going to have to do is to work out what the mass defect is going to be between the two sides of the equation. So I'm going to look at the decrease in resting mass from the left-hand side of the equation to the right-hand side of the equation for the reaction. So let's write down what our masses are. So polonium-218, we know it's got a mass of 361.98198 times 10 to the negative 27 kilograms. The lead-214 Pb has a mass of 355.3252 times 10 to the negative 27 kilograms. And I know that alpha particles coming off, which is a helium nucleus, and the helium nucleus basically has a mass of 6.64591 times 10 to the negative 27 kilograms. So now what I'm going to do is to work out what the mass defect is between these particles. So I'm going to write down my polonium mass, 361.98198, and I'm going to take away the mass of the lead plus the alpha particle, and you'll notice that I've taken out a factor of times 10 to the negative 27 to make it easier. So I get my calculator. I'm just going to put it here so that you can see what I'm putting in. So here is my polonium mass, and I'm going to take that away, and I'm just going to add together my lead mass, 355.3252, plus my alpha particle mass, which is 6.64591, close brackets, and that should equal 0.01087, and remembering that I've got to add times 10 to the negative 27 kilograms. So that's the change in mass. So somewhere I have lost mass. So the key thing to understand is by losing mass, we can now use Einstein's formula of E equals mc squared, noting that a change in mass will be energy released. Now my change in mass, 0.01087 times 10 to the negative 27. C is the speed of light, which is 3 times 10 to the 8 meters per second. So I substitute this into the equation. Just put in the speed of light, and remember you've got to square it. So I'll get my calculator, put in the mass defect, 0.0187 times 10 to the negative 27. I'm going to multiply that by the speed of light squared, and that gives me 9.783 times 10 to the negative 13, and that's joules of energy. So that's the energy which comes off due to the mass defect. Now I know from my question that there's a certain amount of kinetic energy which is given to the alpha particle. Now the alpha particle's kinetic energy had, and let's just check it on the question, there it is, 9 times 10 to the negative 13 joules. So I'll put that down. Alright, so the energy thus has not been conserved because I've got some energy left over. Now as I stated, that energy is going to come off in the form of gamma radiation. The amount is by taking the total amount of energy away from the kinetic energy of the alpha particle. So I've already got that stored, take it away, and I end up with 7.83 times 10 to the negative 14 joules of energy. So this is the byproduct, this is what's left over. So I must include that gamma radiation in my equation to actually make sure everything's conserved. Hope that makes sense. Thanks for watching.